Hello friends. In today's class we are going to solve question related with performance of demand paging. Okay, so let's come back here and we are solving question related with demand paging and this is the first question and it says that if instruction take I microsecond and instruction execution time, you can say instruction execution time is I microsecond and page fault takes additional j microsecond additional, okay, page fault takes additional j microsecond, okay, microsecond. Then effective access time, if the page fault occurs in every k instruction, okay, page fault rate p is 1 over k. Okay, so this is we know that formula here in this case is p, okay, 1 minus p when page fault will not occur. Then here it will take what time it will take, I microsecond it will take, and when the page fault will occur here because it is the use the term additional, okay, it is not saying page fault service time, additional j microsecond. So I'll write here I plus j, and here it will become I, then this will become IP, and this will become IP, and this will become P times J. These two terms are gone and we are left with I plus P into J. And what is P here in this case is 1 over K, and that makes it I plus 1 over K times J. Okay, so answer for this particular question is A. Okay, now here suppose the time to service a page fault on an average is 10 millisecond. Okay, page fault service time 10 millisecond, page fault service time. While the memory access take 1 microsecond, memory access take 1 microsecond. 99.99 hit ratio, okay, a 99.99 hit ratio result in average memory access time, hit ratio, okay, 99.99 hit ratio. Now this hit ratio is for in this particular case related with page fault. So now here the idea is that if there is a page hit, if there is a hit of what, hit of here in this case is TLB, okay, then no page fault occur, okay, no page fault occur. So 99.99 means 0.9999 times no page fault will occur, and in that case it will take 1 microsecond. But here 0.000 and 1 times it has to service the page fault, because that is the miss time, and that time and it is what miss, nothing is mentioned, but we'll assume here TLB miss in this case. Okay, so 0.001 time you have to take 10 millisecond. So this is 0.9999, and this I can say 10 millisecond and microsecond, that means into 10 to the power minus 6 is there, and this is 10, so I'll just multiply this quantity with 10. So 0.00, so this is 10 times, okay, so So this will become 0.001. And again, what I'll do here, I'll just multiply one more time 10 to the power 3 and I write here minus 6. 0.9999 into 10 to the power minus 6, it will become, this will become 1.0 10 to the power minus 6, and that will become 1.9999 microsecond. Okay. Let's discuss this 2011 question, and it says that let the page fault service time is 10 millisecond. Okay, so page fault service time is 10 millisecond in a computer, and average access time is being 20 millisecond, average memory access time, and page fault generated, page fault P is of 1 over 10 to the power 6. Okay, so we know that effective access time is 1 minus P, and we are having a regular memory access, and that I write as MA, and P page fault when come, then we are doing what? Page fault service time. Okay, so 1 minus P, 1 minus P, 1 minus 1 over 10 to the power 6, and we are going to take a regular memory, average memory access time, and that is your 20 millisecond. And P times what we'll do here in this case is page fault service time, and that is 10 into 10 to the power minus 3 into, I'll say 10 to the power 6 into 10 to the power minus 6. Okay, I think I have taken 1 unit wrong. It is 20 nanosecond. Nanosecond. Now if you look at this quantity, this is something like 1 2 3 4 5 6 minus 1 divided by 10 to the power 6, and marginally it will be equal to 20 nanosecond. This quantity will be almost equal to 1. Okay, and 20 nanosecond, this quantity will come approximately 20 nanosecond. This side will become 1 over 10 to the power 6, and this is, let me write 10 into 10 to the power minus 3 into 10 to the power 6 into 10 to the power minus 6, and that I can take it out, and that will become 10 nanosecond, and that will become 30 nanosecond. Okay, so this is an approximate answer, and in this case we'll go with option B. This is the next question, 2018. Consider a process executing on an operating system that uses demand paging. The average time for the memory access in the system is m unit if the corresponding memory page is available in memory. Okay, so if it is available in the memory, then we are taking m unit of the time, m units if page is available. D units if memory access causes a page fault. D units if page fault occur. It has been experimentally averaged. The average time taken for memory access is x. Average is x. Average access time is your x. Which of the following is the correct expression for the page fault rate experienced by the processor? The average access time is x, and 1 minus p is what? We assume that no page fault will occur, and page is in the memory, then it will take m unit of the time, and p times what it will take? Page fault rate, that is d. So x will become what? X will become m minus p into m plus p into d. So what I can take here common in this case is this p I can take common, and I'll left with d minus m, and that will become x minus m. And in this way p I can say is x minus m divided by d minus m, and that is the answer of this question, x minus m divided by d minus m. P is the answer of this. Okay, so that's all for this discussion. Thank you.